Sonia from Group 7 and will be presenting to you about an analysis on sugar refinery process. A sugar refinery is a refinery which processes sugar beets or sugarcane into raw sugar and then refining raw sugar to form white refined sugar. Many cane sugar mills produce raw sugar, which is a type of sugar that still contains molasses, giving it more color and impurities than white sugar, which is a type of sugar that is normally consumed in households and used as an ingredient in soft drinks and food. The refined sugar produced is more than 99% pure sucrose. Raw sugar is either processed into white refined sugar in local refineries and sold to the local industry and consumers, or it is exported or refined in the country of destination. Sugar refineries are often located in heavy sugar-consuming regions such as North America, Europe, and Japan. Since the 1990s, many state-of-the-art sugar refineries have been built in the Middle East and North Africa. The world's largest sugar refinery company is American Sugar Refining, with facilities in North America and Europe. The figure shows the whole manufacturing process flow diagram of turning sugarcane into refined sugar. First, the sugarcane is harvested and washed with water before it was chopped up. The chopped up cane stalks are then crushed and milled to extract the sugarcane juice. Next, a clarification process which involves separation of impurities from the juice by adding flocculants which will react with organic material will be carried out. Then, precipitation of non-sugar debris will follow. The clarification process gives clear juice to be sent to the evaporation process and mud which juice will be filtered further. The clear juice obtained from filtration and clarification process will be concentrated to form syrup called molasses by heating it with a low-pressure steam in sets of vessels called multiple effect evaporators. The syrup formed will also then be crystallized in the evaporators. At this point of the process, the sugar syrup will go through centrifugation that includes a set of centrifuge driven by a hydraulic motor system that utilizes motor-driven adjustable pumps to separate the crystals from the molasses to remove raw inedible sugar. In order to obtain a purer and more refined sugar, the product obtained from centrifugation will go through remelting and clarification again. To get the final product of white sugar, decolorization is also a necessary step. The final step in the processing of raw sugar would then be drying before the sugar is packed and is ready to be sent out. This is the summarized process of sugar production from sugarcane. The three main equipments that our team had chosen to discuss further about are the clarifier, evaporators, and centrifuge.
There are three selected major equipment which contain more control system in this manufacturing process. The first one is clarifier, then evaporator, followed by centrifuge. Clarifier is selected because the amount of flocculant and the juice are needed to be controlled to prevent too much or too little of the amount of the mixture in the clarifier. For the next one, evaporator. This process will gradually convert sugar juice into syrup through a series of evaporators to increase the solute concentration to promoting crystallization process. The steam needed to be in low pressure when heating the evaporator. So, the amount of steam is needed to be controlled to maintain a low pressure of the steam. This process also involves the control of the amount of feed and the water level of the tank to prevent overflow. The last one is centrifuge, which is used to separate the sugar crystal from the mother liquor or molasses. So, Controlling the suitable weight of the mixture and rotation speed of centrifuge are required for the mixture to be separated. The manipulated variable of the clarifier are frequent flow rate, with the controller of flow rate, level, and pH. Its disturbance is raw juice inlet flow rate. For the evaporator, inlet flow rate will be manipulated by the controller of flow rate, water level, and concentration, whereas the centrifuge will have the controller of flow rate, weight, and rotation speed to manipulate the mixture flow rate.
The clarifying process is classified into 3 sub-processes, which is lime addition, carbonatation, and sulfitation. For the lime addition process, the amount of lime added into the clarifying tank will depend on the flow rate of raw juice entering the tank. Based on the research, the optimum ratio of raw juice and the milk of lime is 1 to 3.8 to give higher organic acids removal and precipitation of impurities. Therefore, a cascade control system which incorporates a ratio station is suggested to implement between the inlet of untreated juice and the inlet of lime milk. Since it is a feed-forward control, the offset from the disturbance is removed. Then, we proceed to the carbonation process. The excess lime milk added into the previous clarifying tank will be carried forward into the carbonation tank. The addition of carbon dioxide will reduce the pH of the juice from 11.5 to around 9. The temperature of the process is expected to maintain at around 95 degrees Celsius. A feedback temperature controller has been introduced into this system to control the flow rate of steam into the carbonation tank. Besides, the flow rate of carbon dioxide is being controlled by a cascade control system with pH controller as master controller while carbon dioxide flow rate controller as slave controller. The benefit of proposing cascade control system is that the disturbance from the manipulated variable, which is the flow rate of carbon dioxide, is being removed in this case. Also, the cascade control is applicable in this case as the pH control is a process with slow dynamic which is controlled by the manipulation of a relatively fast process, which is the flow rate of carbon dioxide. In the end, more calcium and impurities are being removed in this tank. The seam of the process control around the sulfitation tank is almost identical with the process control of carbonation tank. The only difference is that the set point of the pH controller is set as around neutral value, which is 6.5. The sulfur dioxide mixes the juice to improve flavor and texture of the sugar juice. The sugar juice is then heated by the steam to drift off any residual gases. The process must be monitored well because an alkaline juice will be produced if the process control goes wrong, causing the sugar crystal to stick together due to moisture absorption, and the sugar would have an undesirable taste. The clarified juice will be proceeded into further process equipment such as evaporator and centrifuge to obtain the final product. Also, a recycle stream is recommended to obtain a higher purity of product. In overall, the main advantage of proposing this control system is that the wastage of milk lime, carbon dioxide as well as sulfur dioxide will be minimized, which resulting into lower operation costs throughout the process.
Now, I'll be talking about the control system for evaporators in sugar refinery plant. In plate evaporators, it is necessary to supply a consistent ratio of juice and steam. In most cases, normal control is to maintain a constant level in the evaporator units, which is done by varying flows between the units. This, however, creates an unsatisfactory flow condition for any plate evaporator stages. A control scheme based on maintaining the juice flows in the appropriate ratios is proposed. The ratios are adjusted to maintain the levels and the required final sugar concentration. This diagram shows the proposed control system. A cascade control is implemented to control the flow rate of the steam inlet to the evaporator by measuring the flow rate of the steam inlet as well as the level in the tank. Since the ratio of juice feed and steam to the evaporator is important, a ratio controller is used to maintain the ratio of inlet steam and juice feed by measuring the steam flow rate and sugar exit concentration. The ratio controller's signal is also sent to the next ratio controller to control the flow rate of the stream by controlling the pump. Two level controls are sufficient in maintaining the fluid levels of the evaporators. In terms of practicability of the proposed control system, the basic dynamics of each evaporator is very fast, and in steady state, the process stream flows maintain nearly constant ratios. Therefore, the control of evaporator needs to maintain the correct relation between the inter-unit flows and maintain the system at steady state. This can be done by rationing the juice flows to the preceding juice flow, with the juice feed being ratioed to the steam input. The levels in the evaporators then can be maintained by adjusting the ratio of the discharged juice steam flow. The ratio of juice feed to steam is adjusted, as in current practice, to ensure the required final juice concentration. The advantages of the proposed control system are that less controllers are needed. This is because the feed-forward control proposed has minimized the disturbance to the evaporators. Besides that, the final sugar concentration can be maintained by just controlling the ratio of steam inlet and juice feed to the evaporators without having to constantly changing the flow rate and causing the system to be unsteady.
The next process control that we are going to talk about is the centrifuge. So, after the sucrose solution have gone through evaporator, the water content will be reduced and form mesacute. Mesacute contains sugar crystal and molasses. Therefore, the mesacute will undergo centrifugation to separate the sugar from the molasses. At start, the speed controller will show 0 reading as the centrifuge is stopped. The signal will be sent to the weight transmitter to begin loading of mesacute for a new batch production. Now, we can see a feedback loop in the highlighted area. The weight transmitter will measure the weight of the basket inside the centrifuge and send signal to the weight controller to begin measuring the offset. Then, the weight controller will send signal to the feed controller to open the valve until it reaches the set point of weight. When the weight of the mesacute have reached to the set point, signals is sent from the weight transmitter to the speed controller to start the centrifugation process. As the centrifugation process begins, molasses will flow out of the centrifuge through its wall and sugar crystal will retain. Flow transmitter at the molasses outlet pipe will send signal to the speed controller to adjust the speed of the centrifuge. For example, when no more flow is present in the molasses flow pipe, flow transmitter will send signal to the speed controller to slow down the centrifuge until it stops. When the centrifuge has stopped, a blade will move and rotate around the wall of the centrifuge to scrape the sugar crystal from the wall of the centrifuge, and then the bottom valve of the centrifuge will be opened to flow out all the sugar crystals. After all sugar crystals have been removed, the entire process flow will start again.